Welcome to yet another episode of Indigenization Appreciation Hour. I'm Saurav Jha, and with me is, of course, my associate, Sriram Tyagarajan. And as always, this is another aerospace focused episode, and we are going to be talking about small jet engines in particular, because that is one arena where, where things are moving much faster than usual, at least in my opinion. For instance, as some of you might be aware, the National Aerospace Laboratories itself has been working on a few turbojet designs. It has been working on a micro turbojet, which is just 50 Newton. It has been working on turbojets in the 1 kilonewton range, and it has also been progressing a design that is in the 2.7 kilonewton range. Now you may think, what is the relevance of turbojets today, and especially small ones? Well, as it turns out, quite a bit. See, the wars of today and indeed tomorrow require mass in precision, as I have mentioned on occasion. They require mass in precision, and for that mass in precision, you need a whole bunch of both ground launch and air launch vectors that will fly, in the high subsonic range, and will not really be. They'll obviously their delivery vectors, they're expendable, but in terms of costs as well, there'll be a huge element of cost management also when we talk about these delivery vectors, because we want to attain mass in precision. They will leverage the fact that all kinds of seekers, whether radio frequency or imaging infrared seekers, have become much cheaper than in the past, so to speak, especially when produced in bulk, relatively speaking, in relative terms, and are more readily available now. They'll also leverage new guidance and navigation and control tools as well. But they will obviously need to be propelled by something which is cost effective as well. And that is where the small modern turbojet, if you like, is going to play a major role. And the turbojets that are currently being developed by NAL, and indeed by some private players in India as well, they are sort of tailor made for those kinds of mission profiles, and for those kinds of delivery vectors. Things that will be produced in bulk will be precise, but obviously will have to be cheap enough so that they can be produced in bulk in the first place. And a turbojet makes a lot of sense in this for this sort of thing, because see, a turbojet is obviously, when you compare a turbojet to turbofan, regardless of whether it is big or small, a turbojet is always less efficient than a turbofan when you talk about flight regimes between 500 km per hour to 1000 km per hour. Right, a turbojet will take something to a lesser distance than a turbofan will, given with all things being equal. This also means that a turbofan can obviously attain greater distances while consuming less fuel. Turbofans are also a lot less noisy than turbojets are, because in the case of a turbofan, as you would know, because of the bypass stream, the bypass jet, a lot of the thrust is coming from the bypass jet, which where the exhaust velocity is much lower than the velocity that is exhaust velocity through the core. So it sort of averages out the total exhaust velocity, and obviously sound is the decibel level of any engine is contingent on that. Having said that, turbojets, of course, have their own niche. Turbojets can fly. Turbojets are more efficient at much higher speeds, and also if you want something to be, they have a lesser cross section than a turbofan. They have a smaller cross section than a turbofan. So if you want something to fit into, say, if you want something to be suitable for the form factor of a, say, a anti-ship missile, which will only fly for maybe 350 kilometers, and will fly basically fast, and will not be performing too many maneuvers or anything, will just skim the ocean surface, will be sea skimming, as it were. Then a turbojet obviously makes a lot of sense, because it will be able to propel it to something like Mach 0.8, 0.9, and also, because the cross section of the turbojet is smaller, it'll help the missile's own radar cross section management. So so on and so forth, or it's the other way around, because the missile is smaller, you plonk in a turbojet there. And the turbojets of today are also designed to be these, especially these small turbojets, which are expendable jet engines, of course. They are also not exactly the way they used to be. We are not talking about jet engines of the kind that were there, say, in the 1980s. Now, these turbojets are pretty much modernized. They have much more reliable start mechanisms. They have, of course, the other thing that is also desirable for mass in precision is making something very reliable and cheaper by bringing down the part count. Now, in the case, one of the advantages that a turbojet has over a turbofan is that the part count of a turbojet is obviously less. It has no fan to begin with. So that is also something that really plays in favor of the turbojet here. And so, what you have essentially is a system that is designed to fit that is designed to basically address the problem sets of today. This is, of course, a turbofan. This is the Manik small turbofan engine. This has a fan in the front, of course, and it has a bypass stream and all that, and it'll have a has an overall sort of nacelle covering the whole scheme in a way. But in the case of a turbojet, that those things are obviously not there. So the thing is that the turbojet can has a lower part count. Turbojets today have modernized materials, which are obviously not going to be the same kind of materials. The material, for instance, the material profile of an expendable turbojet is not what you're going to get on a fighter class turbofan, obviously, which has to be durable, reliable, and has to operate for thousands of at least over 1,000 hours. So it's a different issue altogether when you talk about a turbojet for a sort of a for a small cheap cruise missile or loitering munition that you need to produce in bulk, and you need to deploy en masse, and you need to but at the same time, these small cruise missiles and loitering munitions will also have to, basically will have to display a certain kind of approach speed as well, velocity. It's not like they'll you can just have the small cruise missile fly at Mach zero point 0.5 and be done with it. Even though you're going to launch them en masse, they still have to fly faster, and they don't have to be really maneuverable, unlike, say, something like the Nirbhay LRLACM kind of thing, which will fly, whose flight profile will vary along with waypoint navigation and all that. But in this case, these will fly only for a very short distance, relatively short distance, and they'll have to fly fast, they'll have to fly true, and they'll have to obviously be small. They'll have to have a small radar cross section. So all of these boxes are ticked by a modern small turbojet of the kind that, NAL and other private players in India are developing. So the turbojet definitely has a major role to play in the conflicts of both today and tomorrow, and that is something we must look out for. And these turbojets can be easily built by Indian industry, by the existing supply chain catering to both the Kaveri derivative engine as well as the small turbofan engine, that is the Manik small turbofan, which will power the long range land attack cruise missile, which is currently there up on the screen. So if you can go back to the turbojet again, Sriram, for a second.
Yeah.
And yeah. So as far as these new turbojets go, where I won't belabor the point for too long, they have to have reliable start mechanisms. They will obviously, their part count is lower than a turbofan anyway, but even the small but the fact is that they still require small precision components, and that is something that Indian industry is capable of doing now. The other thing that they have to cater to is, of course, they have to be maintenance free. A turbojet in any case is, requires less maintenance, much less maintenance than a turbofan, because turbofan is a much more complex is a much more complex turbo machine, or a much more complex example of turbo machinery, if you like. So the turbojet ticks all those boxes, as I have already mentioned. And if done well, even something as humble as a small 1 kilonewton turbojet or a 2.7 kilonewton turbojet can have strategic effects. That is basically the point I wanted to make. So, having said that, let us now go on to other things. Shriram is always on the topic of what is going to be the that sort of four engine KD powered unmanned stealth aircraft, which can be used as a regional strike aircraft. So let's see what new thought Shriram has on the subject today, because he always has something going on going on about this.
Yeah, before we get to the larger engines, see, even with the turbojets, it might seem like 1960s technology, 1970s technology where it matured, and everyone was putting one into their small and medium range cruise missiles. The Kongsberg has one, the French Hammer. Uh, those are just a few examples, but it gives you an idea of how useful and how useful turbojets can be when it comes to plonking them into a missile, air launched or ground launched, and it becomes a neat little package that can be so made in the hundreds or thousands. And over the years, as missile developers keep looking for greater efficiency, greater thrust to weight ratio, greater maintainability aspects of the missile itself, right? So the missile sits in a box for years and years, and one fine day it's picked up, assembled, and then it's given a go saying, go and hit this target. So it still has to work, right? So it can't be like the missile has to be taken apart and the engine has to be taken apart and you have to lube every bearing, nothing of that sort. So, which is what, if you've heard descriptions of the BrahMos, for instance, it's called a wooden round, right? It stays inside the canister for years, and then one fine day it's given a target and has to go and hit. So the turbojets were similar. They were asked to do similar things. So having a reliable, cheap, and very high thrust to weight ratio turbojet was and is still a very important ask from any engine or a missile builder. And now that we're moving into these loitering munitions, UAVs, unmanned vehicles, having higher thrust rating turbojets or turbofans is also becoming key. So just calling them decades old technology and why do you need to develop it, why can't you just buy it, is again another let's call it a talking point, and something that must be resisted. Because just like we call UAVs a commodity that needs to be made in the very high numbers, we have to look at the engines or propulsion itself, right? So be it batteries, servo motors, motor controllers, same thing with turbojets and turbofans, the smaller ones, right? Like Saurav was talking about, right? 1, 2.5, 4, all the way up to 10. Anything under 10, I would say they're the smaller turbofans, which will be needed in very high numbers. So, like he said, smaller part count, easier way to build them, be it 3D printing or just casted alloys, where you have multiple parts built in one go without having to screw them together. Lighter weight, cheaper materials. For instance, just like SpaceX went with stainless steel, cheaper alternates have to be found for materials of these engines. All of these are very necessary. So, for instance, Samir Joshi of New Space Research and Technology recently during a seminar said for their unmanned program, right, the Abhimanyu, they were finding it tough to find a local turbojet or a turbofan just under 10 kilonewtons. So there is a need, and there is a need for companies like DG and the other smaller up and coming companies to cater to this market. It might not seem like it's big today, but the future planning today, or the future talk about the future force structure is of hundreds and thousands of these unmanned platforms. So, there is always this risk when it comes to any defense or aerospace, let's say, possibility of a product being required, say 10, 15 years in the future. But there is a significant possibility of such engines being required in very large numbers. So whoever can crack, this market will actually be making a lot of money. So there is a need for all of these, not just for the missiles, the NASAM MR, NASAM SR, NASAM LR, if there is one built, or if the Nirbhai becomes that. But the
No,
NASAM MR will be built in lot of numbers.
NASAM LR will have a turbofan only. NASAM, if it is ever anything such as that is contrived, yeah.
Yeah. For now, the NASAM MR will be a Kongsberg, let's not call it equivalent, but class, somewhat analogous. And even that is like a 300 kilometer, 500 kilometer max range. Anything longer just becomes nearby range, or BrahMos ER, or a future hypersonic cruise missile range. So within that, especially for anti-shipping role, we will need the missile. My fault. A turbojet engine to power it, and all of these unmanned vehicles. Even last week when we were talking about future UAV swarms, loyal wingman swarms, which will fly with your manned platforms, you might have different tiers of unmanned platforms of different weight classes doing different roles. So they might need different engines. I'm not saying this is what will happen, but it might eventually end up there. Just like we have light, medium, and heavy fighters and bombers and fighter bombers, the UAVs might also mature to have multiple layers or multiple tiers, weight classes. So again, you might need different classes of engines, and whoever makes one will be a better position to make variants or another fresh start, however it might be. So again, it's a very key area, and it's not at all something that is, let's call it, old tech that just needs to be built in numbers. There is a lot of work that can be done here. See, industrial capability is a major thing when it comes to fighting wars more than a month, right? So you should be able to source the raw material for all of your high-tech products. You should be able to build it quickly, right? Source it quickly, build it quickly, and push it to the front lines quickly. That is something that all countries so far who've fought major wars really do appreciate. So those kind of things have to be taken care of when you're building for such mass-produced, one-time use products. So the turbojets fit in, right, as much as say small arms ammunition or even artillery ammunition. So these are things where the turbojets are, again, like I said, very, very key if we want to throw numbers at any of our neighbors, right? So going back to the KDE, so sort of
we can. Yeah, let's talk about let's still stay on this topic of small jet engines for a bit longer.
Sure.
So if you talk about small, yeah, if you talk about but however, if you talk about something like an air launch cruise missile, which has a much longer range than say 300 kilometers, has a range of 1500 plus kilometers, then then you have to use a turbofan. You'll have to use something like the Manik, which has probably been made a little lighter than usual, because there are weight penalty issues do matter. In the case of a cruise missile, in the case of a subsonic cruise missile like say the Nirbhay, the weight of the engine does not matter as much when it is ground launch as it does when it is when a variant of the same thing is being launched from the air. Then then weight management does matter, and the fact that the fact that a turbofan will allow something to fly for much longer with a relatively lower fuel, with a relatively lower amount of fuel, is something that will matter there. So when it comes to long range cruise missiles, whether air launch or even ground launch, it's the small turbofan which will matter, not the turbojet. So the turbojets that are being developed today are being developed essentially for loitering systems, loitering munitions that are not going to loiter, in the sense that they are of, ideally speaking, if you want something to loiter for a longer duration also, you need that bypass, right? Because that's a much more efficient way of sort of flying in the subsonic regime. So a turbofan would be called for, but no, but these are not the kind of loitering munitions that loiter forever. If one were to think that, these loiter only for a bit, actually, and a turbojet is suitable even for them. But turbofan will again is again more suitable for something like, say, the collaborative combat aircraft that are being developed today. Which is why in the previous episode we emphasized on this. We emphasized the point that sooner than later we'll see the say the new Hellcats Warrior switch to a couple of turbofans, because it makes more sense. Because it's not going to fly in just one kind of regime. It's not going to fly at the same kind of speed and at the same altitude. It has to mix it up a bit. Even though the schemes that you've seen till now for CCA seem to suggest that they will stick to a very narrow flight regime, but I think that sort of CCA will not prove as useful as people had once imagined. That they are not going to prove as useful as people had once thought they would. So anyway, having said that, with Shriram has of course put up a picture of the KDE now. The KDE is the Kaveri derivative engine, and there is much to be said about it. We have talked about its salient features in the previous program. In this program, we'll talk a bit about some of its producibility aspects. Now, as you know, Godrej Aerospace is currently integrating six of these engines for GTRE from 8 different modules. And that is something worth noting, because the first two engines, which have been tested extensively, and one of which and have been tested at the high altitude engine test facility in Russia also, those ones were integrated by GTRE itself. But the ones that are going to see delivery this year are being integrated by an Indian industrial partner, and it has 8 different modules. It has a fan and disassembly. There is an intermediate casing. There's of course a bypass duct. There's compressor, combustor, turbine, jet pipe, and exhaust cone. These are the modules essentially. In all, the KDE has over 800 parts and assemblies. Right. So it's a pretty substantial piece of turbo machinery. So it's something that anyone, it obviously, whoever is integrating the KDE at this moment will fancy their chances in the as an industrial partner for more substantive or more complex efforts that are currently in the works. So as far as the most complex effort that is currently in the work is obviously the one for a fifth generation engine, a follow on to the whole Kaveri, but with a completely new core and etc. A lot of the work that was done on the fourth generation Kaveri will of course serve as a stepping stone for the work that will be done on the fifth generation engine. But the fifth generation engine as such has very advanced features in comparison to a fourth generation engine. Can we put up that slide, Shriram, which shows
Yeah.
the differences between different generations of engines? I think that is
Yeah.
pretty useful.
Yeah. Yeah. Go ahead. I'll put it up.
Yeah. Okay. So the thing is that
Yeah.
now, as far as this fifth generation engine is concerned, obviously it will have a new core. Which will have to cater to a much higher turbine entry temperature, right? Turbine entry temperature, which will be at least 200 to 300 sort of kelvins more than what you have
Yeah.
in the case
That's
of
on
a
the
fourth generation
x-axis.
engine. Yeah. So, and also the thrust to weight ratio will have to be 10 or above. you have all these features put up nicely in this one chart that was shared by GTRE. Then, of course, the propelling nozzle will have to have a thrust vectoring. You'll have to have a thrust vectoring scheme over there, not just a simple convergent divergent nozzle as you have in many fourth generation engines. And the control system will have to be an intelligent control system, not fully intelligent as in AI enabled as in the case of a sixth generation engine, but it will have to have integrated engine and flight control. It cannot be standalone. So, and of course, fan pressure ratio greater than 4.5, that's typical. And bypass ratio is also higher than what you have in the case of a fourth generation engine. The bypass ratio usually in the case of fifth generation engine is anywhere between 0.3 to 0.5. So those are the and to basically to meet these specifications, India at the moment is looking at a co-development partner. And as we have said before, the co-development partner should ideally be one that itself has a great amount of pedigree in the jet engine space, but does not have a working fifth generation engine at the moment. That is the kind of co-development partner we should choose, because that is the kind of co-development partner we would probably be able to leverage better than others. So anyway, let's not harp on that point in this episode. But the fact of the matter is that we should see we should, if India really wants to become an aerospace power, it needs to become an aero propulsion power. And to become an aero propulsion power, it needs to be able to field a fifth generation engine of its own in the 2030s. For that, work has to begin this year. So ideally, or rather hopefully, we should see some forward movement on this front in this budget itself. Right, that is our hope and expectation here. We at DDR feel that something has to be done in the if we have to move forward. And obviously, to move forward, these things require investment, which obviously means that, which in turn means that the Ministry of Finance has to take a favorable view of things. And hopefully the Prime Minister's office and the Ministry of Finance will take a favorable view of the need to invest in a fifth generation engine as soon as possible. And by as soon as possible, we mean this year itself. So let's see what happens. Let's see what happens, on that front, whether we hear anything of this or not. And if we do, then of course it means that the country is beginning to move forward as far as the aerospace domain is concerned. In the meantime, or rather meanwhile, the focus will of course be on the Kaveri derivative engine, because it is supposed to power a particular platform that we have talked about in the past. And the focus will obviously also be on all these small jet engines which are less than 12 kilonewton. Usually, when you talk about a small turbofan, you talk of something that is between 3 and 12 kilonewton, and you usually don't design turbofans that are below 3 kilonewton nowadays. I mean, then you settle for a turbojet because of all the factors that we discussed in right at the beginning of the program. A turbojet then makes a lot of sense. A modernized turbojet, obviously, not a turbojet designed in the 60s. A modernized turbojet with much better starting mechanisms, better gears, so on and so forth. So with all that, with the whole small engine space that we've looked at, and the KDE, we are currently in a state where we are doing all right as far as powering delivery vectors and certain medium-sized platforms are concerned. Medium as in not a medium-sized fighter platform. Let's say smaller platforms are concerned. With the right amount of time and investment, these engines will all be ready in this decade itself. But the question remains, the question as always remains the same. What are we going to do about our fighter class turbofan requirements? And we not only have to focus on a fifth generation engine, sooner than later we will also have to work on a sixth generation engine. But you cannot really jump from being a country that has produced a fourth generation engine that has only been tested on a flying test bed to one that can suddenly produce a sixth generation engine. The fifth generation engine, therefore, is a sort of a, a sort of a bridge over there before you can really enter the realm of sixth generation variable cycle engines, which nobody has really entered credibly as of now. I mean, America is the world leader in it. China is trying very hard, and Russia also has something. But like I said, in terms of durability, whether the Russian effort will really be a sixth generation engine or not is an open question. There is a school of thought which says it doesn't matter as long as an engine meets all the performance criteria. It doesn't matter if it isn't that durable or not. Having durable engines is old school thinking. The Chinese will simply produce thousands of not so durable engines and keep swapping them in and swapping them out, right? Unfortunately, the life is not quite so simple. The logistical challenge of an ever increasing number of engines is not easy to manage, and you can also have critical engine failure at the wrong time in the middle of combat if you sort of, if you forsake durability. Because because when you forsake durability, you forsake engine reliability also. It's not like, you can have a super reliable engine that is not durable, because after all, it's about the material characterization. It's about the materials that you put into the engine, right? So the issue of being able to fabricate parts out of those materials and fabricate parts which are near net shape is a critical issue. And so, just as there is the design aspect, there's a whole design aspect when you talk about a fifth generation or a sixth generation variable cycle engine. There is that critical manufacturing aspect as well. And for that critical, to ensure that you're ahead of the game as far as that manufacturing aspect is concerned, you need to secure critical materials, you need to secure your critical material supply chain. Again, this is something that is best done in collaboration with others, given the environment we have today. Nevertheless, we must also become serious about mining and refining aerospace grade materials here in India, and metal, and certain, obviously I'm talking more on the metal side of things. Those are the things we need to focus on. For instance, today Indonesia is the biggest producer of nickel in the world, and China has locked in a lot of that nickel supply. We also have a lot of nickel, by the way. We don't really need to import nickel as such. Nickel, we of course lag behind as far as the processing of
Processing.
nickel is concerned, right? So that is something that we need to now work on in a concerted manner, and that too requires investment. There are a number of institutes around India that have
CSIR
these,
institutes.
exactly, CSIR, and also other institutes as well. Even some even university funded labs are there. All of these need to be brought under a single umbrella and energized with the right amount of investment and personnel. I think Sriram has a lot to add over here, so I'll just, give it over
Yeah.
to him.
We've
Yeah.
we've had a lot of labs and government institutions who have worked on ore extraction, ore beneficiation, ore processing, and mineral extraction out of these whatever sources we have. Unfortunately, like a lot of our research attempts, they've been half-hearted. People who've wanted to do a lot of progress in these areas have been outright ignored, been underfunded, not given any importance. So when you look at our mineral and ores exports, we export a lot of just plain ores without doing a lot of further processing. Now, for any country, rather than exporting raw material, if you process the raw material and sell it, you get better value. So when people talk about value add, right? So even for the let's call the PLI schemes, what value add are companies adding over just importing the components and putting them together, right? So that is a common way of criticizing the PLI scheme. Now, for something as critical as ores, it becomes even more important, because you shouldn't be like India under East India Company, where you're selling cotton, right? The fabrics and the clothes get made somewhere else, and then this clothes get sold back to us at a premium, and we lose our industry, our know-how, our entire livelihood of people who were doing this before they were brutally pushed aside. So this is the modern form, right? Earlier it was muslin, now it is products made out of our own minerals. I think there was a instance that Abdul Kalam had recounted in Wings of Fire, I think, about the Japanese sanctioning us and us stopping beryllium exports, right? If it is in that book, I remember, please do read it. It's very very interesting. Now, coming back to the Japanese themselves, right? So they have the technology to build permanent magnets, and they wanted to tie up with IREL for us to sell them the ores, and they would do all the extraction, processing, and then manufacturing of magnets, and they said we'll sell it at a reduced rate and all of that. It never progressed to a large degree, but I'm saying, see, this is what happens even for iron ore from Karnataka, for instance. From here we sell a lot of iron ore. Why aren't we building specialist steels? Right now we have a PLI scheme for special steels and special alloys and all of that, but never got done, right? So we're having to do it now after so many decades. It's the same thing with critical metals, right? We talk about a lot of these metals which are key for a lot of modern industry, be it semiconductors or aerospace: gadolinium, germanium, neodymium, a whole set of metals. We'll do a critical metals and materials IAH very soon, maybe after the budget, because it's a very extensive thing. So coming back to where we started, right? So we need all of these organizations to be really empowered, give them specific goals. I mean, once again, you need not criticize them saying you are trying to reinvent the wheel. Nobody is giving us the wheel. You might see that the other guy is having a wheel, but that does not mean that you have a wheel, right? So reinventing the wheel is not so bad as people make it out to be, because you don't have one. The other guys have, and they're not willing to share. They're willing to sell you wheels, right? But you can't build your own wheels for your own chariots. Otherwise you'd have to fight on foot. But that is something that people seem to paper over, right? So like he said, Saurav said, all of these entities have to be brought together, given specific goals, enough funding, enough facilities, and asked to solve certain problems for which today import is the only answer, right? And that plays a major role in our aerospace and defense ecosystem, because materials are key, apart from all the other components, of course. But this is the basis. One single metal, if you can't import, an entire system cannot be built. So this is as key as any other facet of the whole industry, and this definitely needs to be addressed. And another point, coming back to the engines, right? So there was even a question. Let's just address the question along with this. Now the French, which are most likely our engine partner going forward, right? Rolls-Royce is going to make a bigger engine for a bigger GCAP platform. Not sure about the French, but our need is the slightly bigger than the 414 class of engine. We really don't know what Rolls-Royce and the Japanese want to make. And assuming it's the French, and they don't have a 5th gen engine, and there is let's not call it informed talk or with any serious basis, but there is this now that we are aware that you have variable bypass engines and it is a possibility and that somebody has done it, I'm sure that is also on the roadmap for whatever engine co-development deal that we're going to sign. Saying we will have graded targets for our engines. We will first build a fifth gen and then build on it to get to variable cycle. It also means that we need to start programs for research into variable cycles so that we don't have to depend entirely on somebody else giving it to us, even if it means we do co-development. I hope we now understand the scale of work that needs to be done, even if we have a co-development framework with somebody else, with an OEM who has built engines.
Yeah, if you think of it, as far as the low pressure turbine and yeah,
Go ahead. Go ahead.
okay, okay. So as far as the low pressure turbine and the combustion chamber part and all that is concerned, I think that is well within GTRE's current capability set. It's basically the high pressure turbine part that where you need hand holding probably because
Even
you
the
need. Yeah,
combustor for the newer
yeah, yeah,
designs,
yeah,
staged
yeah,
combustion
yeah,
and everything.
yeah. If you need stage combustion, I agree with that. So the thing is that.
Even they have said that it is a huge area of research and there's a lot of work that needs to be done, and
Yes, yes,
CFM has
yes,
done it in the CFM
yeah,
Leap engines, so
yeah.
Safran has good expertise in that.
Yeah, but Leap is still 2013, right? So the kind of things they're looking at right now, you probably require more work as you outlined at the outset. So that is correct. I don't deny that at all. So there is a lot of work to be done there, even with a even under a collaborative, even as part of a collaborative effort under a collaborative antenna. But coming back to the issue of critical materials, one thing I just want to highlight is you need an entire bureaucracy. Although people will say, why a bureaucracy? No, you need a bureaucracy. You need a bureaucracy that basically presides over the indigenization of things down to the sixth and eighth digit level, right? When I say 8 digit or 6 digit level, I'm of course talking about the harmonized system nomenclature, HSN code, that is used by the World Customs Organization. For instance, suppose you are importing something, you are going to import using these codes basically. So for instance, 8103 is the HSN code for tantalum and articles thereof, including waste and scrap. India might manage that today, no problem. But HSN code 810320 is for unwrought tantalum, including bars and rods obtained simply by sintering powders. That too, I think we'll manage. Then you have, nowadays you have these 8 digit HSN codes as well. 81032010, which is tantalum and articles thereof, including waste and scrap, unwrought tantalum, including bars and rods obtained simply by sintering powders, and in addition to that, hollow bars. So it goes like that. You see, that is the level. That is how the complexity increases, and that is the kind of detail. That is the kind of attention to detail you need. That is the kind of level to which you need to go down to if you want true indigenization and you want true independence in the aerospace domain. I'm just giving an example. There are any number of other things that have to be looked at. So we as a country, India now has to understand that aerospace development is not simply a function of what kind of collaborations you get, or what the total size of your economy is, or so on and so forth. It is not merely a function of that. Obviously investment is extremely important, being able to recruit the right talent is also extremely important, but even more so is the management of things, how things are managed. So there has to be a single authority of bureaucrats and technocrats who work together to manage this very critical national development program. Because without your own aero engines, you are not just not an aerospace power, you are not really going to have the kind of geopolitical independence that you want, as
You
we are
won't be any
already
kind of
seeing.
power.
Yeah, that is by extension, that is what it
Yeah.
is by extension, right? So this is a domain that needs to be licked, and we have to go stepwise. We have to first start producing all those small expendable turbojets and turbofans that we talked about. Then we have to produce the KD in numbers, right? And we, at the same time, we have to launch into this collaborative effort with a trusted partner to develop a fifth generation engine. So that is how we are going to do it going forward. At the same time, we must also work to indigenize the engines that are already there in our inventory. I need not elaborate on this further. Some work in this domain has already been done in the case of the Russian AL-31 FP and the RD-33 MKs and all that. But this has to be also be a core strategy going forward. In a sense, this is a way in which you de-risk programs, because today you have the manufacturing capability to indigenize something which indigenize a proven fourth generation design from somewhere. So this should also be looked at as a possible contingency plan. It should not be off the table, because otherwise we cannot end up being in a situation where we just aren't able to produce any domestic fighters because they're dependent on the engine supply from elsewhere. And our existing fighters also, fleet also, we can't keep in the air because somebody is blackmailing us. It should not be like that, right? So this is something that we need to look at. Again, these are things that are best managed through a proper process, right? So we can elaborate on what that process could look like in the future. Maybe an aero engine commission is the way forward, like you have an atomic energy commission with absolute high level access straight to the prime minister's office. That could be one answer, right? So, but that is something we can discuss threadbare in a later episode. So now I think, Shyam, we could
Do some
perhaps turn to a
questions?
few questions. Yeah, turn
Sure.
to a few questions.
Let's see. Okay. Darsh Dubey, sort of related, right? Can you tell an somewhat accurate timeline of the Amca? So I'll take a go first, then sort of you jump in whenever. Um, See, Dr. Ghosh, who's the project director, program director earlier, he said from the date of sanction, it would take anywhere between 3 to 3.5 years for the prototypes to start flying. And it would be a full-fledged prototype with radar, EO systems, an engine, I mean, the F414, and all the other associated technologies that the Amca Mark 1 would fly with. Assume 3.5 to 4 years, and it was sanctioned this year, last year. We still have another 3 years to go. I would say we just have to wait. The sanction has come after much teeth grinding and back and forth and a lot of fighting. So it has happened finally. Now it is the time for all the agencies involved to put the heads down and get it out. The Mark II, for instance, is expected sometime later this year. If that flies on time, then that will give us confidence on Amca's progress. Other than them doing and showing it to us, there's no point in asking and getting insider views and trying to say it is on the test, jigs, and it is getting built. And this product, this subcomponent is going to fly in tomorrow, and it'll be ready in 2 months. No point. Let it come out, and there is a very good hope that it will come out in the timelines that they've mentioned. But again, they have to do it.
Yeah, yeah, the new timelines, that is, which is the timelines that are followed on from. Yeah, Shyam, I can't hear you for some reason.
Yeah, it's on. Go ahead.
Okay. So yeah, so the new timelines. As far as I'm concerned, I think we will see AMCA flying before general elections 2029. Right. So we will definitely see something there.
Yeah.
Right. So no, I'm not for a second suggesting that it's linked to general elections 2029 in any way. I'm merely saying that we are going to see it before that. So that is where we are at the moment. And as far as the Tejas Mark II is concerned, I think we should see it flying within the 10 to 11 months from now. For is my hope. Is not just my hope, is my expectations also. Is my expectation rather. Is my expectation. Now let's take some of the other questions. We have
Sure. We
we
don't have
have
much time.
Akshay Iyer. Yeah, we have Akshay Iyer saying thanks Saurav and Sriram for restarting the series. Yeah, we thank you as well for joining in. Don't you know? Don't you know? We think we do good research, but we fail in mass production of engines. Yes, well, that's precisely the point. That's what we discussed all this while. That mass production is a different ball game altogether. Mass production requires the kind of attention to detail that we delineated just a few minutes ago in this program. But you're very right, and this is something that needs to be highlighted again and again and again. It's not a question of inventing things. India invents things. I think some startup founder who's become very popular now was talking about how we need to invent fighters and drones. We have already invented those. The real question is whether we will be able to produce them at a rate or not. And in the case of whether for better or worse, in the case of airborne platforms, not having the key subsystem, which is of course the engine, the propulsive unit of that say of said platform at your disposal, is obviously a deal breaker. You will not be able to produce anything. So while in many other things, if you have design control and you have design control, and you have, even if you have 60% indigenous content levels, it's absolutely fine, or even less, because you can indigenize, subject to of course minimum order quantities becoming better. In this critical domain, the propulsive unit is actually much more important than the aircraft itself, right, in this domain, than the platform itself. And but of course this doesn't mean that that you look at wholesale imports altogether, because that gives you no options at all, right? That just about anything, not just the fact that just about anything can be denied over there. The engine itself can be denied also, if the whole thing is wholesale and you're completely reliant on somebody else's supply chain. So it is always better to build your own platform and have an increased indigenous content over time. But in the case of aero engines, we have the country has to launch into a massive indigenization program forthwith. Enough time has already been spent in discussion. I think it has to be done this year.
Yeah.
Shyam, your thoughts on
Yeah.
this?
It's the same thing, right? So unless you have your stranglehold on a lot of critical steps in making whatever you're making, you will end up getting squeezed by whoever has a handle on one of those key components without having a complement stranglehold on their supply chain. You understand what happens, right? So, and remember, unlike say the OECD countries, the Europeans, Japanese, South Koreans, and the Americans, and even to an extent the Australians, we are not at the same level. We are not as pally with the Americans and the Europeans. Look at the American 3-tier list for GPU exports. That is a clear, let's say, an image of who your friends are. The Americans consider us not as part of their closed, circle, but as a friend who can be trusted in sometimes. And the Russians and the Chinese is somebody who can never be trusted, right? So that tells
we have too much pigment, Sriram. We have too much pigment.
Correct. So that tells you, right? So in push comes to shove, whether you can depend on all of these guys to supply, or them to play their own games using us, is the question that needs to be answered. And I am sure everybody understands that it's a very simple answer. Asmodeus, I think that answers your question about the MRFA also, right? Karthik MK, who I think just joined as a member. Thank you.
Yeah, thank you for that.
Is the AL51 engine feasible in Su-30 MKI? The HAL chief had recently gone to Russia. I'm pretty sure they had engine-related talks there based on whatever can be a drop-in replacement for the AL31FP. It depends on what the Russians want for it. First-born child, second-born child, or maybe all of your children, right? So It has to be feasible. I'm sure they have a drop-in replacement because they have a huge fleet of Su-27s and Su-30s, the Russians themselves. They would like to have a modern engine to replace them. The AL-31 is a very old engine, right? It was built in the design in the 70s and 80s. So I'm sure they would also love it if we come and give them a lot of money to fund their own engine re-engine program.
The drop-in replacement can only be the AL-31FN, and I don't think anybody is interested in that. So
Whatever
that
can
is
be,
that is the drop-in replacement.
Okay.
That can be the drop-in. Because when you talk about re-engineing an aircraft, you're talking about a whole set of things that you need to address. Starting with the issue of whether your intakes are optimized for the mass flow of that particular engine or not, right? Or can at least cater to the mass flow of that engine or not. So there are the whole bunch of issues that have to be addressed before you can, So it's not plug and play. You can't plug and play engines, unfortunately. That's the other issue. Although in the case of the AMCA Mark II, the AMCA Mark II will be ready for this fifth generation engine, will be kept ready, right? So for the fifth gen to be able to so that its airframe is able to accept the fifth generation engine that will be ready by the 2030s if it begins development this year. So mid 2030s. When I say 2030s, I mean 2035, 2036, because it will take at least 10 to 11 years to get that ready to a place where you can put it onto an operational fighter. So that is the state of affairs. We have Austin, of course, who is extremely generous and sort of contribute something in every other program, as I have observed. So he has some observations as well. He's
Thank you
saying,
so
"Thank you,
much.
Saurav and Sriram. Thanks to you, and thank you to you as well. Ukraine war has shown us the importance of having a strong industrial base to support war. Or yes, absolutely. We should focus on 100% indigenization, including engine of MKI Tejas. MKI engine we won't be AL-31FP. We won't be able to indigenize because of the simple reason that the contract was sort of inked in such a way years and years ago that certain things will remain perpetual import from Russia. So that is not something. So in terms of indigenous content levels by value, we'll attain about 63% with this current tranche of engines. That is the target sort of indigenous content level for the 200 AL-31 FPs that Hal Koraput is going to build now under a 24,000 crore program, and it'll have to complete the order in 8 years' time. So by 2032, all those have to be completed. So that is where things stand. I see that there have been these incipient wars going on in the comment space over here. We'll not get into that. But somebody
We'll go
asked,
to another
yeah,
question.
yeah.
Quick question. Data Adda, will you guys be at Aero India? Yeah, I will be there with a couple of guys from our team. Saurav is skipping this year. We'll catch up next year at Defense Expo if it happens, hopefully in Delhi.
Yeah.
What is the status of the HTFE 25 and the HL engines, HTC 1200? Last we knew, the HTFE 25 has the core has finished bench testing, and now there is a full-fledged engine undergoing testing on a bench in Bangalore. They have HAL has a detailed plan on how many engines to build, what to test, and how to test, and when to test. And as for flight test beds and high altitude facilities, I think the hope is by the time the engines mature to be to require these facilities, something will be available in India. That is the hope.
HTFE 25. It's a low risk program, really.
It can even be put on a transport aircraft and flown test.
Yeah. So it's not really an issue. There's an interesting question here from Utkal Ranjan Sahu. If HAL can build HTSE 1200, why not build a 500 to 700 kilowatt class turboprop engine? You're right. If you have credible capability in the turboshaft domain, you should be able to use some of that for a turboprop as well. But turboprop development is right now happening at NAL, and I think the focus going forward will be a 4000 to 5000 HP turboprop. That will be a spin off from that fifth generation low bypass turbofan that we are talking about. Also, somebody, I think, last in one of the previous programs, now I'm reminded of that, asked about this cone shaped thing in front of the HTFE 25. Why is it larger than usual? That is a design choice. That is, of course, called a spinner. That's called a spinner. And spinners are used for for two main purposes: to direct the airflow at a certain angle into the air duct, and also to prevent foreign object damage. These are the two main purposes of the spinner. Now, why the HTFE 25 has that peculiar large size cone? Maybe they're really worried about foreign object damage, and maybe given there are and also they probably have certain considerations as far as the airflow is concerned, which in any case is a consideration for putting a spinner. So those may be the reasons why it has a larger than usual spinner. But spinners are pretty much there being used across the board. Even the EJ200 has a spinner. The what do you call that? Many large engines, many of the high bypass turbofans continue to have spinners. So it depends. It depends. There are many trade-offs. The shape of the spinner, whether it is more angular or not, whether you want to make it more angular or not, is also a design choice. So there are many issues there. We could discuss that sometime when we talk about, when we discuss parts of modern day jet engines in detail in some program in the as in the in the forthcoming weeks or months, as the case might be. So anyway, with that, I think we'll have to conclude this episode of Indigenization Appreciation Hour. Thank you all for tuning in. And as Sriram mentioned, he's going to be there at Aero India, and there are other some of our other team members will be there with him as well. And in general, we will of course bring to you whatever we can, whatever is shareable from Aero India, and you will have greater visibility on many of our indigenous programs going forward. With that, let me conclude this episode. Jai Hind.
Thank you. Bye bye.